Hello, everybody. Welcome and thanks for joining this talk. My name is Wen and I work at Microsoft on the SMB development team. And today I would like to talk about some new features involving the security of SMB3 over RDMA. So in 2021, we introduced support for RDMA encryption over direct data placement. So if you recall, before 20H1, if you wanted to send or require encryption or signing in SMB, and you're also using RDMA protocol, so SMB will resort to sending the data in either write requests or read response, depending on your I/O. So instead of taking advantage of the actual direct data placement, it's taking this slow path of just sending everything with the request or response. So that actually performed significantly worse. So in 20H1, we added encryption support to go through the direct data placement. And then we also added some 256-bit AES encryption algorithm support. And then for RDMA signing, it is not released yet, but it's in the feature complete stage. And we also added support for the AES GMAC algorithm. So as an overview of what is direct data placement, so the general idea is that you want to offload some of your transport stack to the RNIC so that it won't cost any CPU cycles on your client and server when, like, during this transport of the message. And then generally how we use it is you would register a buffer with the NIC. So essentially you're passing the ownership of some memory buffer from the OS to the NIC. So it's ready to be sent or be read or written to. So and then once you register the buffer with the RNIC, once you pass this ownership, you will get some descriptor token. So this is completely opaque to SMB, but then this is needed for the remote party to either write to or read from that buffer you registered. So therefore on the left hand side, this is an example for an SMB write. So what we do is the client will register the buffer that it wishes to send. So it gets the token. It sends the token along with the write request. So once the server validates the request and the token, it will instruct the server RNIC to issue a RDMA pull request to pull the client buffer into a destination buffer that the server specified. So this is the direct data placement process. And then, so this process does not cost any CPU on either the client or server. So then when the DDP is finished, server will get a notification and then it'll perform the actual work to write the data to the down-level file system. And then after everything finishes, it'll issue a write response to let the client know that it's okay to deregister the buffer. So this step is kind of like reclaiming that ownership back from the RNIC to the OS. So for read, it's very similar. But other than server doing an RDMA pull, it would be doing an RDMA push to the buffer that the client registers with its RNIC. So for encryption and signing purposes, what we need to do is to make sure that the content of the buffer, for example, for write, the buffer, it needs to be either signed or encrypted before registration. And then for read, server needs to so sign or encrypt before it does the RDMA push. So for on the receiving end for write, server needs to be able to decrypt or validate that message, and so is the read on client. So client, or so is the read. A read for client, client must be able to decrypt or validate the message. So then because the encryption algorithm that we support are all authenticated encryption algorithms, which means it'll both sign and encrypt the message. It therefore generates a signature and a nonce with the encryption. So, and we need to inform the other party of these metadata in order for them to successfully validate or decrypt the message. So for SMB write, the design is just to send those metadata with SMB2 write request, and then for SMB read, so the server needs to send the metadata with a read response. So next, let's take a look at the protocol updates. So because for this feature, both the client and server needs to be enlightened, we added a new transform or new negotiate capability called the RDMA Transform capability. So, and this notice that this is not only for encryption and signing. This can be used for any future transforms we support on SMB messages on the direct data placement messages sent through SMB. So therefore, we have a variable length of RDMA transforms at the end of this negotiate context. So then this is a protocol, like a view of what the message would look like when you send a encrypted write through the direct data placement. So you have your familiar SMB2 header, the write request. Then you have this what's called the SMB2 RDMA transform struct. And then what's following that is a list of transform descriptors. For example, we have encryption, and anything that's interoperable with encryption can be also added in this list. So in this, and then in the end, you obviously need your, for write request, you need your RDMA descriptor you got from the SMB Direct module. So in this design, think of the SMB to RDMA transform as like a base structure. It has it has some common metadata that no matter what transform you do, you would need, and then think of like all the transforms as, so whatever is performed on the message needs to be, so those any metadata that those transforms generate needs to be included in this this transform descriptor list. So let's look at what's in the SMB2 RDMA transform. So first we have RDMA descriptor offset, length, and channel. So if you're familiar with the SMB2 protocol, you might recall that these are actually also present in the write request. So you might wonder why this is also needed here. So the reason we have another set of the RDMA descriptor offset, descriptor length, and channel is because we introduced another RDMA channel called the RDMA transform to the SMB protocol, but not to the SMB direct protocol. So when this channel is used, we assume that the sender is using RDMA direct data placement with transformed messages. Therefore, the channel, the descriptor length and offset in the SMB2 write request struct must be used to locate the entire metadata range as shown in this diagram. And then the channel value on the write request will be set to RDMA transform, whereas the RDMA length and offset, RDMA descriptor length and offset on the RDMA transform struct in this struct will be used to locate the actual RDMA descriptor consumed by SMB Direct. And then the channel value in this struct will also be either V1 or V1 with the remote invalidation, which is also consumed by SMB Direct. And in addition, we also have a transform count. This is because it is possible to link as many interoperable operations as possible for one message. So the receiver will expect this amount of transforms in this transform descriptor list. So next we take a look at the RDMA encryption transform that we introduced in 20H1. So for each node in the list, we expect a transform type to identify this type of what type of transform this is. And then for encryption, we need to include signature and nonce in the message. So we support a variable signature and nonce length in this design as opposed to a fixed 16-byte signature nonce length as in the SMB transform header. So therefore, in addition to specifying the length here, we actually need to put the signature, the actual signature and the actual nonce after these 8 bytes. And in the end, if this struct does not end on the 8-byte alignment, we need padding to make sure this struct is 8-byte aligned. So at the very end is the RDMA descriptor as we've seen before, and then so the requirement of that is it has to begin on a 8-byte aligned address. So, and we in the protocol design, as mentioned earlier, make sure that that requirement is fulfilled. So I think this concludes our discussion for the protocol changes. And as far as management changes, there shouldn't be anything needed due to that encryption and signing are, for the most part, requirements instead of optional transforms. So any existing encryption or signing configuration would automatically utilize this feature as long as the server and client are both updated to receive this feature. So then let's take a look at the performance of this feature. So in the experiment, we used 2 machines with 50 Gbps bandwidth of RDMA bandwidth. We limited our CPU to 4 cores and 4 threads. So the idea is we want to bottleneck the CPU and then see how much throughput with these different security requirements and with the different builds, see how much throughput they can push through. So in the red column, it is the performance of encryption over RDMA before 20H1 release. So And then we would compare that to the green column, which is the encrypted RDMA performance in the 20H with the 20H1 release. So for write, you can see there's a very good throughput increase around 3x, but for read, it's only maybe around 1.5x. And this is due to a known improvement on the parallelism needed on the client side when we receive encrypted encrypted read messages. And this is just for RDMA only. So, and then for the signed performance, we would look at the yellow column and the light blue column. So the yellow column is so before, without this feature, so blue column is with this feature, although it's not released. So we used some privates to get these numbers. And as you can see on right, it's also a pretty good increase, about 3x. On the read, it's also about maybe 1.5x due to the same performance improvement needed. And on the dark blue is reference when we send the plain text direct data placement. So next, let me demonstrate this feature, and then we will answer any questions we have from the audience. So let's start with the demo. And so we have a client machine and a server machine. And this client machine, it's a TK53WP03R0413. And the server machine is the same string, except that it ends with 1515. So we're remoting to the server machine to create a new share. So keep in mind that in our test environment, we use the RAM disk on the server to eliminate the disk bottleneck. So the F drive is actually the RAM disk. So we're now creating a share that is gonna be encrypted. So we require encryption on this share. So then next, we create a share that is signed only. So we do not require encryption, but we set the registry key on the client to require all the traffic to be at least signed. So as you can see in the Lemon workstation parameters, the required security signature is set to 1. Now we exit the remote session from the server, so we can start creating a file on that new share. Let's start with the encrypted share first. So we will create a relatively large file. So this is actually going through encrypted direct data placement, but it's not the speed that we saw in the previous slide yet because it's a create file operation. So it's using less queue depth as we did in the that slides testing. But now we will use 32 queue depth, and as you can see, we are approximately sending 5 gigabyte per second. So which translates to 40 Gbps. Now let's try a read. So there's a slight delay in the UI, but we should see the result momentarily. So we see that the average speed is around 2300 megabyte per second. So now let us delete that file on the encrypted share to leave space for the signed for the signing test, for the signing demo. So actually we can just create another file on the signed share. So same, we use 50G and then 1 megabyte. So, and as stated before, this is create file, so performance is, well, it's more that we are not sending that much I/O, but let's do a write. So as you can see, we achieved more than 5 GB per second. So it's expected because it's doing less work than encryption. So let's do a read. And then, so again, UI delay. Okay, so our read is around 3200 megabyte per second. So this concludes our test on the new code. So now let's take a look at the performance of the previous behavior without this feature. So we're using the exact same environment, other than that the binaries have been replaced by the previous binaries without this behavior. So we're going to look at the performance of encrypted and signed traffic using packet-based I/O instead of direct data placement. So we use the same size. So this is actually being encrypted. As you can see that the throughput is much lower, although we're not using QDEP32 yet. While it's doing the create file, let's take a look at the registry key to ensure that we still have signing enabled. But keep in mind, this experiment we're doing now is for encryption. We're just checking the registry key for signing in the meantime. So now let's do write with buffer size 1 megabyte and then QDEP32. So it's around 1500 megabyte per second. So let's remove this file to make space for signing. Sorry, there's a typo. So we can just change the share name. And finally, let's make sure the QDEP is 32. So we see around probably a little bit less than 2 GB per second. Again, expect it to be faster than encryption, but then slower than using direct data placement. So I think this concludes our demo. So thanks again for joining, and we actually have plenty of time left if there are any questions from the audience.